Computers are just like other electronics. They understand only electrical signals. You can think of these signals as a string of high and low voltages. But for simplicity, we represent them as ones and zeros, known as binary, where a 1 can be a higher voltage and 0 can be a lower voltage. We call these ones and zeros the language of machines, and they tell the hardware what to do. Those binary ones and zeros are also known as machine code. They are the native language of the computer's hardware. But writing machine code directly is like trying to communicate in a language made up entirely of numbers. It's super difficult for humans to work with. To make things a bit easier, there's something called assembly language. You can think of assembly as a kind of dictionary that represents machine code in a more readable format. For example, let's say we want the computer to add two numbers, like 5 and 3. In machine code, this might be represented by a binary string like this. Remember, ones and zeros shown in the machine codes. From the very foundation, they are just electrical signals, where 1 can mean a higher voltage and 0 can mean a lower one. As you can see, they are very hard to read, right? But in assembly language, we can describe those exact same instructions in a more readable way. Remember, by nature, assembly and machine codes are the same thing. It is just assembly more user-friendly to communicate with a computer. Let's investigate how machines codes or assembly work. Before we dive into the details of these instructions, let's first understand how a computer performs addition. Inside a computer's hardware, there's a component called an adder. This adder takes two inputs and produces a single output. To perform an addition like 5 plus 3, the computer needs to first load the numbers 5 and 3 into special storage locations called registers, which are directly connected to the adder. Registers are small storage areas inside the computer's hardware where data is temporarily stored. There can be multiple registers in a computer. For simplicity, let's call the first register %0 and the second register %1. Let's recap. These are machine codes or instructions sent to a computer to perform 5 plus 3. And these are the assembly which describes the same instructions in a human-readable format. Now, let's break down the instructions one by one. For the first instruction, the first 4 bits represent the move operation, which tells the computer to transfer data. The next 4 bits specify the destination register. In this case, the destination is the %0 register. Finally, we have the binary representation of the number 5. So after the first instruction, we have loaded number 5 into register 0. By the same token, the second instruction will load number 3 into register 1, and the final instruction will invoke adder to perform addition. In summary, assembly language and machine codes are actually the same thing. They are the native language of computers. Assembly language gives us a manual or a guide to the binary instructions. It's much easier to read and write in assembly than machine code itself. But assembly is still not as simple as the high-level languages we usually prefer today. For example, here's how we can achieve the same addition operation in 2 high-level languages, C++ and Python. Notice how much simpler it is to write and read. So, in this lecture series, we will see how those high-level languages transition into assembly instructions.